On April 12, 1961, Soviet cosmonaut Yuri Gagarin piloted a 2,400-kilogram spacecraft in humanity's first manned space flight. 1 week later, Bell Aerosystems debuted another advancement in aviation, the gas-powered rocket pack. Capable of flying 35 meters in just 13 seconds, the rocket pack thrilled onlookers, but the device's engineers were less enthused. Despite years of cutting-edge work, they knew this short flight was all the rocket pack could muster. So why was a massive spacecraft easier to send flying than a single pilot? According to Newton's laws of motion, the physics behind flight are actually quite simple. All you need is a powerful enough upward force to counteract the downward force of gravity. And since objects with more mass experience stronger gravitational forces, lighter objects should be easier to get off the ground. However, modern jet engines, our primary tool for flight, actually get more efficient the larger they are. Jet engines work by sucking in huge volumes of air and then expelling that air as quickly as possible. While most of this air actually bypasses the inner machinery, it still contributes to a huge portion of the engine's thrust. But the air that does enter the engine's core gets compressed by a series of tightly packed blades. That compressed air then enters the combustion chamber, where it is injected with jet fuel and ignited. The heat causes the compressed air to rapidly expand, bursting out of the exhaust and propelling the engine forward. As air leaves the engine, it also turns a turbine embedded in the exhaust nozzle. This turbine powers the fan and the compressor blades, creating a cycle that maintains thrust for as long as there's fuel to burn. The more air an engine can take in and expel, the more thrust it can produce. On a modern jet, the diameter of a frontal fan is larger than a truck, and even spinning at relatively low speeds, these engines produce more than enough thrust to maintain the necessary speed for flying a passenger aircraft. But smaller engines simply can't take in this much air. For most of the 20th century, engineers couldn't produce an engine small and light enough for an individual to wear, yet powerful enough to lift itself alongside its pilot and fuel. Designs could only carry enough fuel for 30 seconds of flight, and when airborne, the powerful thrust in a single direction made jetpacks difficult and dangerous to control. But the new millennium brought advances in materials, manufacturing, and computing technology, including systems which could manage fuel injection with incredible precision. Together, these dramatically improved the fuel efficiency and power-to-weight ratio of jet engines. By 2016, micro-engines the size of a coffee can and weighing less than 2 kilograms could achieve 220 newtons of force. This was when an English engineer named Richard Browning saw the opportunity to create a new kind of lightweight jetpack. In addition to a single engine strapped to the back, this so-called jet suit involved a pair of micro-engines on each arm to split and balance the thrust. Working with the back engine, these provided 3 points of stability, which some pilots describe as being akin to comfortably leaning on crutches while a friend supports your back. It may seem complicated to manage all these engines at once, but many pilots master it in less than a day, with the help of another advanced computer system, their brain. Various brain regions and multiple sensory systems perfectly calibrate our sense of balance and spatial orientation, helping pilots smoothly direct their flights. Slight movements of the arms allow operators to increase and decrease lift, quickly turn in midair, or glide forward for up to 5 minutes. This technology is still fairly new, and without major advances in fuel efficiency and engine technology, don't expect to have a jetpack of your own anytime soon. But if reaching for the sky already got us this far, who knows where we'll fly next?